Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great honor and pleasure to welcome PALLE Jorgensen from the University of Iowa, who will tell us about coherent states of q-canonical commutation relations. But before giving him the floor, let me say that we are very happy to have him aboard because he is a person you would typically meet in a library via his textbooks. So it's wonderful to have him in person. PALLE, the floor is yours. Take it away.
Thank you very much, and thank you for the kind invitation.
Hello.
And Marek Bożejko just joined in.
Oh, I'm Marek is here. Okay, good.
Hello.
Okay, yeah, I'm so happy
nice
to get
meet
at least
you.
a wave to Marek.
Nice
Yeah,
to meet you. Good condition.
Yeah.
So
And
you are
so
in Poland or you are in America?
Yeah, right. And I should say again that the general subject in the title of the talk here owes a tremendous amount of pioneering work by Marek Bożejko and by Bożejko and Spiker and a few more pioneers I will mention. And Marek Bożejko just sent me an email that he has still exciting new things in the general subject. Okay.
Thank you for nice words, PALLE. So we wait for your nice.
Right. Yeah. So Marek and I met one another a long time when I visited Poland, and I guess we met at other conferences too, and our work has a lot of common ideas and common interest, and so that is true in particular for this, especially the q-canonical commutation. Now, the subject that I'll be talking about has its roots both in quantum physics and in functional analysis and in non-commutative analysis and C-star algebras. And among the C-star algebras, we will be looking at the ones that are especially well known. Are three of them, and they are named, the two of them named after commutators, and that would mean canonical commutators and anti-commutators. And then there's one in the middle that's that is closely connected to the CUNTZ algebra, and so that would be the general framework for us. And maybe I should just mention one more connection to quantum physics, and that is that so in quantum physics you have quantum states and then you have quantum particles, but in physics a particle has a dual life. It's not always a particle, it's sometimes a wave, and so I'll keep that in mind. But whether you give it one interpretation of the other, its properties are determined by commutation relations, and in the beginning there were just two of them, sometimes called fermions and bosons, and I'll mention those. And then because of the physics of those, it became interesting to explore a continuation in a parameter. So you, instead of having just commutators and anti-commutators corresponding to q equal to 1 and q equal to -1, you look at all values of q in the open interval. And so now you get qons in addition to the fermions and the bosons, and qons play a role, and there are other ons in physics. But I should say that my own work started with my collaboration with a mathematical physicist by the name Reinhard Werner, and he's in Hanover physics, and he is especially well known for identifying entangled states, and that's usually a difficult problem. It's related to the stuff that I'll be talking about, and there are even special entangled states that are named after Werner, the so-called Werner states, and its connection to classical physics and the EPR experiment and so on and so forth is something that I probably won't be able to get into. Okay, so that I always say when I give a talk, I should explain the words in the title of the talk, so that at least I've done that. And so this particular abstract here is a little condensed, And so parts of my slides are from one of my joint papers with Reinhard Werner. This one here is, and they're all mentioned in the references that I'll get to at the end of the talk here, and I'll say a few words about them. This one here is in the journal called Communications in Mathematical Physics, because it has many connections to mathematical physics. Okay, but the other thing that I like to state as a general fact about the very complicated details on this condensed abstract here is the role played by three different interpretations. If you look at the first two lines, you have what's called the q-commutation relation. And if you take q equal to 1 or minus 1, you get the more familiar ones. The more familiar ones typically on the right-hand side would have just 1 times the scalar product instead of 1 minus q. And the reason for the 1 minus q would become clear later. It leads to many more solutions and they're easier to manage. But as you look at what we now call the q-commutation relations, you should think about it just as an algebraic construct, but it's based on a Hilbert space H. And then the q-commutators can be compared to the inner product coming from that Hilbert space H. So you start with the Hilbert space and you develop an algebraic construct. And so, of course, if you have two fields, let's call it A of F and a dagger of G, then you have two simples indexed by elements in the Hilbert space. I've not mentioned where they should be realized, but that's kind of a key thing about representations. The moment you have an algebraic relation, the next question is how do you represent it by operators in a Hilbert space, because this is a conference on operators in Hilbert space. And so, right. So if and we'll be talking about how to construct them, but suppose you have a representation, that means the abstract elements that you're looking at here will then become operators. So if the operation is called pi, then you'll apply pi to these operators. So you'll apply pi both to the A elements and to the A dagger elements. And part of the condition that's required for a representation to get C-star algebras or other star algebras is that when you apply the representation to the dagger element, you get the adjoint operator. And that's actually one of the two reasons that I use the dagger notation here. One is it helps us remember when the element is just an abstract element in an algebra or whether it's an operator. And if it's an operator, I guess in operator theory, we usually call it a star. So to be more precise, pi applied to an A element adjoint would be pi applied to the dagger element. The dagger notation, again, comes from some special representations that are popular in physics. And we'll be looking at a bigger class of representations and the distinction between the special representations from physics and the more useful ones that we need in this discussion here for understanding the role of isomorphism of C-star algebras is as follows. Now, in physics, you always like to be able to visualize what's going on. And so in the physics language, the Hilbert space H we're looking at would be called one particle. And if you tensor a family of vectors from H, then you get a tensor monomial, and that would be called whatever the degree of the tensor polynomial is. It'll be called, if the degree is D, then it'll be called D particles, and so on and so forth. And so if you want to construct representations, then the abstract algebra that we're looking at here would have to be represented by operators in some Hilbert space. So the question is, where do we get the Hilbert space? And so historically, what people did in physics is they just iterated these tensors. And and so let me just say the baby version of the Fock space is where you iterate tensors and make it in the simplest way we can. So obviously you can take tensor monomials by the generating vectors from the Hilbert space H, and then you can have creations indexed by a single vector, and that just means that you kick in that single vector in your tensor monomial, so it gets one slot longer, and that's why that operator is called the creation operator. It creates a tensor factor. In physics, it would mean that it creates a particle and so on and so forth. But the adjoint you would expect should go the other way, so it peels off a tensor factor. How do you peel off a tensor factor? You apply the inner product with a single vector to the tensor factor you want to peel off. Now that's just the general intuition, but the next thing is you have to pick the Fock space construction that's relevant, and so that could be the symmetric tensors, and those are the ones I just mentioned here, or the antisymmetric, or the QAnon tensors, and we'll get back to that in a minute. But before I do it, I want to say that the symmetric Fock space has an other connection, both to mathematics and physics, and a third connection is to stochastic analysis, because there's a historic way of realizing the L2 space built on as a path space construction with a probability measure on the set of all pairs. Think of them as Feynman pairs or some other path, and so that would be the third connection that I would like to mention, and that turns out to be very important because the early developments by the pioneers was motivated by how to deal with a modification as you vary the Q variable here to the so-called Pauli exclusion principle. So if you have states and particles, or the particles could be wave functions, then the fermions have the property that a state cannot be occupied by more than one particle. And so that seems like that you, if you want to modify that to take into consideration photons or perturbations, then a natural way to do it is to vary the Q parameter. And so if you take the Q parameter to be close to the fermion case, then you would expect some different kind of Pauli exclusion principle. And that's still a completely open question of how to make that precise. But some of the early work on that and later work as well that I've done too in quantum probability is that you then develop a Q analog of the path space measures that are more traditional in Feynman calculus, et cetera, et cetera. Okay, so that was that.
May I ask you a stupid question?
Yes.
You wrote here that this universal sister algebra has a
Yes.
largest proper ideal.
Yes.
So should I infer from this that there are a number of different of such largest proper ideals, and by whichever
Yes.
you divide, you get the same result?
Yes, absolutely.
Okay.
So that would be a point that I'll get to now. There's two answers to that, and one is a short answer with a yes that I just gave you. But for the purpose of being explicit, there's a canonical maximal ideal that we'll be paying attention to, and I'll be able to point to it. This is what it is, and we'll get to that in a moment.
Excellent.
But the role of that ideal, while we're at it here, maybe I'll just elaborate a little bit. The role of that ideal is similar to something that people have done in operator theory for a long time, and that would be the tuplets algebra.
Exactly.
And,
yes.
the tuplets algebra is an extension of the continuous functions by the compact operators. And so I'll be looking at what's called CUNTZ tuplets or q-CUNTZ tuplets.
Mm-hmm.
And the CUNTZ tuplets is an extension of the CUNTZ algebra by the CUNTZ tuplets algebra, and then a similar by the compact operators, and a similar q analog of that for all q that lie between -1 and 1. So the absolute value q is strictly less than 1 here. So that I'm glad you asked. Please, everyone, just ask, because the subject is big, and I'd rather concentrate on things that address specific questions that come from the audience. Okay.
Thank you.
Then the next question is, how do you get your representation? So I already said you can do Fock representations, and I did some hand waving about what they are. It turns out when you pass to this universal, then that cannot be realized as a Fock representation. So you have to do something completely different. And so that's the difference between the Q version of the CUNTZ tuplets as opposed to the q-CUNTZ relations here. And so the q-CUNTZ algebra would be the universal one that comes from after you divide by the ideal. And that does not admit Fock representations. So it's only before you mod out by the ideal that you get the Fock, and then you have to do something else. And so line 3 is about that something else. But line 3, I should also emphasize some notational hand-waving or simplification, and that's popular certainly in the math physics literature. When you go to a representation and you have an algebra, you should really write pi applied to the elements. So in line 3, it just says A of f applied to some element. But what I really should have said is that I'm looking for a representation of that algebra here for a specific q, and the representation should be realized in a new Hilbert space, not the one-particle Hilbert space, but in some new Hilbert space that should be the Hilbert space of the quantum universe, subject to the Q relation. So that would be a much bigger Hilbert space. And so then when you look at line 3, you should think about these as pi applied to the generating A of f elements. And so that would be an operator, but I ignore the pi for notational simplicity. And there's a raised hand. Could someone read the question?
Yes, I have a quick question. So this one particle space is a real Hilbert space or complex?
Complex, very important. Thanks. And that'll be clear later. That'll be clear later. I'll call attention to when it comes later. For some discussion, real would be okay, but there's a particular discussion where it'll be absolutely essential that the initial Hilbert space H in line 2 is complex. And so if you have a representation, then you have this magic Hilbert space where the representation is acting, and that typically is much, much, much bigger than the initial Hilbert space, which, if you're a mathematical physicist, could think of as a one-particle Hilbert space. Now, we talked about the Fock representations, and they have creation and annihilation. And so if you keep annihilating the particles, then eventually you get to 0, and you have to kill it, and that's called the ground state. Now, the coherent representations are not ground state because you don't kill the vector omega, but what you do is you make omega a joint eigenvector for all the operators A of f, and the eigenvalue will be the variable vector f inner product with the generating vector. So the representation that I'll be looking at here would be indexed by single vectors in the Hilbert space H. So think about them as one particle. And so then what you all of a sudden have here is you have an indexed family of representations of the Q relations. And so one of the theorems that we'll get to as we continue will be how to construct these so-called coherent representations. So the coherence is again from physics. The inner product is a measure of coherence of the waves that have a quantum wave function representation, and so that's the role of the inner product, and that's another instance where it's important that the inner product is complex. And so that was that. But a big part of the paper that I'm reporting on and some of the discussion later would be constructing these coherent representations for every Q and study its properties. But to begin with, since the representations are indexed by by single vectors phi like this, the obvious question is the properties, if the norm of phi is less than 1, if it's equal to 1 or bigger than 1. So let's take them one by one. If the norm is less than 1, the representation turns out to be unitarily equivalent to the ground state representation, which is a Fock representation. If the norm of phi is equal to 1, we call them the peripheral vectors, or the corresponding states, the peripheral states. And that, and of course, I should mention that for everything we do by way of representations, we make use of GNS, Gelfand-Norman-Segel, which is the way of doing correspondence between positive linear functionals, which in mathematics are called states on the one hand, and representations on the other hand. So in line 3, I give the representation, but in the further discussion as we continue, you will also see the corresponding states and the role they play. I should say also for the construction of the standard Fock space, you have various n factorial and binomial coefficients. And so for the Q relations, you have to have Q versions of those. And the construction of the symmetric Fock space here depends on a Hilbert space exponential. So if you have a vector in the single Hilbert space, you tensor it with itself n times and divide by n factorial, and that's called the Hilbert space exponential, and that's easy. And then there's a Q version of that, and I'll be getting to that shortly as I continue with explaining things. And but if the norm of the generating vector phi is equal to 1, then all of a sudden you get something completely different. You get that these representations, so-called peripheral representations, will not be realized in the Fock space. That's number one. Number two, as you vary the peripheral case, so that means as you vary the vector phi with a unit norm, you get mutually singular representation. So you get a countable family of mutually singular representation, and that's very important, because in many of the classical theorems about Fock representations,
there is a question. Adam has a question.
Yes.
Yes, in fact, 2, but all of them are quick. I hope so.
Yes.
I'm a little bit confused by this 1 minus q. For q equal to 1, you get something which is commutative. Am I right?
for q equal to, that's interesting. No, for q equal to 1, you have a dagger is equal to a dagger a. Okay, right, yeah, okay, so right, yeah, that's true, yes. So then I think you have an excellent point here. For most of the literature here, it's traditional to, instead of having the factor 1 minus q, having the factor 1, because if you have that, then you get the canonical commutation relation. So you might wonder, why in the world does he put in 1 minus q if you want to connect it to the canonical? And the reason is the following. From the physics literature, we know that A of f and a dagger of f in the canonical commutation relation are unbounded operators, and we want these elements to generate a C-star algebra. And so we get better analytic continuation properties if we do this version here. But in our earlier paper, we have a version that has a factor 1 on the right-hand side instead of 1 minus q. But in that case, you get singular behavior because as q goes to 1, you get into the unbounded operators. And so that, but
I have a question that we have
yes,
only
yes.
one slide, abstract, or maybe I only, or everybody.
No, I'm moving on. I'm just spending a lot of time on just that one slide.
So it's only abstract one. Okay.
Okay, here the next.
Okay.
There exists more slides.
And sorry, I have also
Okay,
one
thank
more
you.
quick question
Yeah,
about this D. D is the dimension of this initial Hilbert space, yes? The one
Yes.
particle space. Okay, thank
Yes. So that dimension can be 1. It and I'll be talking about that. That's called the Q harmonic oscillator. It can be D. In that case, you get CUNTZ algebras, OD, or it can be D infinity, in which case you get more interesting physics examples. So the Hilbert space H is important, and even its dimension being 1 or finite bigger than 1 or infinity would play a role in what I'll get to in a moment.
Let me also comment very quickly, Adam, look, if f is equal to g in this equation, in the first and second line, then you simply get the Klimek-Leśniewski Q relations for the Teplitz algebra.
Yes, correct,
Yeah.
absolutely.
And this is definitely nicely bounded.
Yes, that's right.
You see?
So the reason that we used 1 minus q instead of 1 was that then we didn't have to worry about the unbounded.
And also, guys, please ask questions at will. Don't wait for me to give you permission to ask a question. I mean, of course,
Yes,
try to be polite and not disruptive, but don't wait for me to tell you.
But I'll appreciate that when there's a question that
Of
someone
course, people are listening.
right, yeah, because I'd have trouble clicking on many different things while I'm giving the talks.
Sure.
Okay. So I think I covered the main summary here, and so maybe as a second part of the abstract here, and I have to apologize that I spent a good chunk of time just on the abstract, but that's because it's a nice way to summarize the key points before we roll up our sleeves and go to the technical details involved in the key points. And so some of the key points is the limit as you go to the fermions and the bosons, and there's a lot to say about that, and it depends on whether you use the factor 1 minus q or 1 on the right-hand side in Q relations. And then there's q equal to 0. That's a connection to the CUNTZ algebra, but both the CUNTZ both the quintuplets and the quotient by that canonical ideal that I'll mention shortly, and then the Q version of the CUNTZ algebra, and that's again you can have a canonical ideal and you can mod out by the ideal, and you get a Q version of the CUNTZ algebra. And then finally, the big question is when is the Q version of the universal universal Q, when is that isomorphic to Q equal to 0 to the standard, more familiar CUNTZ algebra? And that the answer that I'll stress here is that if the absolute value of Q is less than the square root of 2 minus 1, there's a conjecture that you can do better than that. And there's some work on that conjecture that I'll also try to summarize. However, as you attack that conjecture, it makes a big difference whether you attack it just for the Fock representation of the Q relations, which is much easier, as opposed to the universal Q CUNTZ algebra, which is much, much harder. And so the result that I report on, which is joint with Reinhard Werner, is that for the universal Q algebra, we have isomorphic to the canonical CUNTZ algebra when absolute Q is less than square root of 2 minus 1, which is 0.41 or something. So it's a good chunk smaller than the endpoints. And so we kind of conjectured that you have isomorphism in the whole open interval, but different people might have different expectations on that. There's no reason to expect that the square root of 2 minus 1 is special. I was told by Voiculescu a long time ago, so this initial work here dates back quite a while. I was told that he had several of his PhD students try to improve the size of the Q interval where we have isomorphism. And he says that none of them managed, and so they had to get a second thesis project, he told me. Okay, so questions about this? So I apologize for having spent a good chunk of time on that, but I think it's a good thing because it's a way for me to introduce the basic notions. So with those basic notions, you can better make sense of such terms as are mentioned in these 3 bullet points here. Actually, it's more like 10 bullet points here. And so the first bullet point, and then from now on, that will be what we mean by the Q relations or the Q commutation relations. And so, as I said, they have different interpretations: pure algebra representations, representation theoretic representations, where you have to distinguish between Fock representations or coherent representations, and canonical C-star algebras. And so that was where the conjecture came in here. So that was the first bullet point. The second bullet point is the one that comes from physics, and for that, we should use the different version of the Q relations here, because the Q relation for Q equal to 1 in physics would be the canonical commutation relations, and those are for both statistics, maybe for physicists to interpret it in the language statistics. The bosons Q equal to 1 would be the symmetric statistics, and for Q equal to minus 1 would be the antisymmetric, and then for Q strictly between them, it'll be a Q version of that, and the Q version of that is called QANZ. So the speculation of the physics of elementary particles that are subject to the Q commutation relations. But those would be the ones that allow unbounded operators. But I want to restrict attention to bounded operators, so that's why I used the factor 1 minus Q that some of you asked about, and that's very, very nice. And so I mentioned one important is that the Pauli exclusion principle is easy, and you can realize it in experiment. But what if you take a small perturbation of making Q a little bit bigger than minus 1? Then how do you modify the Pauli exclusion principle that you realize in an experiment? And so that was one of the motivation for looking at Q in the open interval. And what else? Right, and so there's some early work on that. Spiker has some fantastic work on that, involving a quantum probability and then giving a quantum probability interpretation of the Q relations when Q is bigger than -1. And so that was one, and so that kind of stochastic interpretation involves a Q version of stochastic calculus, and that's what the next bullet point refers to. And the last bullet point is the one that I mentioned again, how to realize these relations in a canonical C-star algebra, and to get a canonical one, you have to pass through a quotient, and I'll get that in a moment. Questions about that one here? Then I go to the next one. The next one is also, and so the Bieden, Hahn, and McFarlane are cited in the papers that I list at the end of the talk, especially the ones with Reinhard Werner. And I guess if you have a single generator, you can get a Q version of the harmonic oscillator, and so that was one of the motivations. And then another motivation comes from the case when D is equal to 2, so 2 generators, and then the Q relation here, and it turns out that the Q relation for that is directly connected to a quantum group in the sense of Aronovich, so I'm not going to talk much about quantum groups in case you haven't heard the name quantum group. First of all, it really is not directly related to quantum. So you know that for a commutative compact group, the irreducible resonance are one-dimensional, and so you get a dual abelian group here. But the set of irreducible representations of U2 or other non-commutative compact groups is not itself a group, but it turns out that if you define a group functorially, and if you reverse the arrows that you use in the definition, the functorial definition of a group, then you get an other object which fits into what goes by the name a quantum group, and so they have they play a big role both in math physics and in operator algebras.
We are very happy with quantum groups.
Oh, good. Yeah, right. Yes. And so of course, the quantum groups have a long history, but the early paper was Voronovich in the late 80s, and many people work on those. Okay, so there was that. And then the next bullet points here is the unilateral shifts and the Bose creation in physics. Now, for these 2 bullet points, I'd like to make a parallel to the Wall decomposition. So Wall decomposition says an isometry is a direct sum of a unitary and a shift. Now, there's kind of a Q version of that for a single generator. And for the Q version of that, the shift becomes a weighted unilateral shift, where the weights are for as you move forward in the levels in your shift here, the weights become the square root of 1 minus q to the n. So that is a direct role of the Q parameter in the way the operators are represented. So if you represent the vacuum with a single harmonic oscillator, then you just get the shift without a weight. But for the Q, you get a weight, and not only that, the weight turns out to be the square root of 1 minus q to the n, so the weight moves ahead. Okay, so I'll get to that too as we move.
Tomek has a question.
Yes, I have a question. If you could back, yes. The second line after Biederhardt and McFarlane introduce there's a word oscillator starting with hyphen. There should be Q. And
yes, Q. Yes, okay.
Okay.
Thanks for spotting a misprint. I think last time I looked at them, I think I found five. So extra points for spotting misprints. Thanks.
Okay. Sorry, I have a question about this Q. Could be this Q function or some free parameter, or this is a constant only?
For much of the discussion, it's a constant, but in a few slides further along the way, I will actually introduce a field of C-star algebras, and for that, the parameter might play the role as a direct integral parameter. But for most of what I do, Q is just a constant. But for building direct integrals of Q-ons, it would play the role of a continuous parameter.
Thank you.
Let me make a quick comment. It's not very related to your talk, but it's related to Tomek's question. There's a very interesting example of Matsumoto quantum spheres, three-dimensional spheres. And over there, this parameter theta can be taken a constant, and then it's like this irrational rotation C-star algebra constant.
Yeah.
But because you can have this, and now please forgive me my Danish, Heerot splitting.
Oh, right, yeah.
Heerot splitting of a three-sphere.
Yes,
this is given by the gluing of two solid tori. When you have a solid torus, of course, you have many of tori nested one in each other, and then you can vary this parameter theta from one torus to another, and then indeed the deformation parameter is a certain function.
Yeah, absolutely. I've always been fascinated whether those questions have direct connection to Voronovich's quantum groups, and I don't know the answer yet. But that, I mean, all my friends in topology, they're very fascinated with that. By the way, the Danish pronunciation is Higor.
Higor. Thank you so much. It's always my problem. Higor. I love this guy because I'm using his math, but it's so tough to pronounce. Okay, Higor. Okay.
Yeah, right. So right.
So let me return the favor. It's Voronovich, not Voronovich.
Oh, good. Right. Yes. So right. So I guess maybe the Danish language and Polish language have one thing in common: no one can pronounce them.
Well, there's one more thing in common. We use the word tak, but in Polish it means yes. In Danish it means thank you.
Oh, that's right. Yes.
And it leads to very funny misunderstandings, let me tell you. But let's not waste time for this.
Yeah, good. Okay, so that was history, and I think it's better that we have discussions, and if I don't cover everything, that's perfectly fine. That one we already did, and maybe the new thing is I'll get to talk about that canonical two-sided ideal and equivalence versus singularity and irreducible. So I mentioned that the peripheral coherent representations are irreducible, and for different unit vectors, so for different peripheral representations, you get them to be mutually singular, and mutually singular can be expressed in two ways: that they are realized in orthogonal invariant subspaces, or that any operator from one space to the other that intertwines the two representations must be zero, and so that and so it's analogous to infinite product measures, where again for infinite product measures you have the Kaktani dichotomy theorem that either they are equivalent or they're mutually singular, and so there's an analog of that for these coherent representations that I'll be talking about. And so for the case when the generating vector is a unit vector, then different unit vectors give us mutually singular representations, meaning that they live in orthogonal spaces. And so if they live in orthogonal spaces and there's an index parameter q, then you can use that for direct integral, and that's one case where the direct integral plays a role. And Greenberg again is very important, and I cite the papers at the end of my paper with Renner.
Sorry, may I have a question?
Yes.
There's a quick question. I don't understand this condition, living in orthogonal spaces. If you have a representation, then it acts on some Hilbert space, but this space is somehow constructed abstractly, yes, for a given.
Yes. So here's the definition. You have two representation, and you want to know if they are orthogonal. And if you can find two subspaces so that the first one is invariant under the first representation and the second one invariant under the second representation, and when you restrict to these subspaces, you get isomorphism, and in that case,
equivalence.
Yeah, right. And
equivalence of sub-representations, yes.
Yeah, right.
So, okay, so this
right.
makes sense. So I think that it is called sometimes disjoint, being disjoint.
Right. Yes.
So
I use I use the term disjoint too. Yes.
Okay.
So there are probably two or three other popular names in representation theory, but in the theory of unitary representative Lie groups, the equivalence classes of irreducible representations is a big thing, and sometimes it has a Borel structure and sometimes it doesn't, and so that's an important thing here. And there's a parallel to that. I always use questions here as an excuse to elaborate in a related question. And the related question is, you could ask, what are all the star representations of the CUNTZ algebra after you do equivalence classes under unitary equivalence? And the answer is that it's very big and it cannot be classified, and it doesn't have a Borel cross-section. So there's not a Borel set that intersects every equivalence class at one point. And so that's another thing that's special about the CUNTZ relations. Did that help a little?
Yes, but sorry? If I could comment, so this is specific for every sister algebra which is not of type 1, yes?
Yes.
The existence of the Borel cross-section.
So, right, yes. So the CUNTZ algebra is purely infinite non-type 1. Mm-hmm.
So the existence of this Borel cross-section is something like being close to commutative, not exactly commutative, but being close to commutative.
I wouldn't say that, because the semi-simple Lie groups are type 1 and there's a which.
Okay.
Okay, but then
can I say if you one sentence about Greenberg?
Yes.
Because I met him personally in conference in Poland, in Karpacz. Probably people in Poland know. There was mathematical physics conference, about 80, and he believed that exists that Q particle when Q is very small to 1, but less than 1. He don't believe that Bose, Q equal 1. But he couldn't show, so he posed me problem, and we show with Speicher. He divided only for he couldn't prove that Q to the number of inversion is positive definite. So and we proved this with Roland, but he posed that question, and I don't know, you wrote that is how he come from Pauli principle will be interesting for me. So you have some material, please send to me, because now is your talk, okay? But
yeah, right. Yeah,
very good to remember Greenberg and his conjectures, and that in Poland.
Absolutely.
It was in Poland, Karpacz conference. Yeah, thank you. So I've been.
So I should also say that a lot of what I'm talking about is heavily motivated by pioneering work of Marek Bozhenko and also Roland Speicher.
Thank you.
And some others. Yeah.
Yeah.
Okay.
We also
Okay.
follow your ideas when you extend it to QIJ relation, that you
Yes,
extend
right.
it to CUNTZ, to Coxeter relation, and so on. Anyway, so this is
That's
another
also
story.
exciting. Yeah.
Maybe I
right.
have time to Piotr Hayat seminar. I be speak more about this. Recently, we're
Fantastic.
doing for the Coxeter of type B, so it's sign permutation group. Anyway, but this is another.
Oh, good. Okay,
Yeah,
that's
yeah.
exciting.
I
No,
will not
I'm
interrupt your
very
talk.
happy
Yeah.
to learn all
Only
this. Yes.
I'm
Thanks
happy
a
that you
lot.
mentioned Greenberg because he was
Yes.
very clever
Yeah.
mathematical physicist, of course. He was not.
But he also kind of asked all the right questions.
Yeah, yeah. Thank you very
Okay,
much once
okay,
more.
thanks very much. Yeah, okay, so here the quantum noise and Spiker, and I don't have time to go into details, but those of you who are interested in quantum probability, I just heard from Spiker a few days ago that he's right now working on Q versions of quantum probability. So there's a lot of exciting things going on in that. And so I mentioned that in classical in stochastic differential equation, you have a noise term, a Gaussian, a Brown motion, and so on. And so the quantum one are Q versions of that Q Brown in motion and so on. And that's a very exciting direction, but I'm not going to talk about it. And the single generator case I already mentioned, the quantum group one which so the Q deformation of the quantum SU2 group. Okay, and then we mentioned the weighted shift that for the Q harmonic oscillator, the way
Could you please go to the previous slide?
Yeah.
Just for a moment.
Yes.
Representation in quantum groups or of quantum groups?
Up.
Yes.
So
okay.
you spotted another typo. Thanks.
Q and 2 were interchanged.
Yeah. And so I apologize for the typos. And right, and so multivariate operator theory is another connection here. And again, the weighted shifts are forced on us for the Q relations, and the weights will be the square root of 1 minus Q to the n. And here's another typo. It should only be 1 Q, not 3. But the bullet points, I already discussed the bullet points here. But I want to emphasize again then that when we do the Q Fock space, it's a very important construction, and you get the Fock representations here. But the coherent representations that I mentioned in the abstract in the beginning are not realized in Fock space. And the conjecture about isomorphism of Q algebras has different answers, whether you look at, for the two cases, when you look at the universal Q version of the COMMUTATIve relations, or if you look at the Q relations in Fock space. So the questions are easier in Fock space, and you have a bigger interval in the Q variable where we have isomorphisms if you just look at the Fock representations. But my emphasis here will be the universal C-star algebras. Okay, and so I already mentioned that the Q triplets algebras arise with central extensions. So the Q CUNTZ algebra will be the Q triplets algebra will be a central extension of the universal CUNTZ algebra by the compacts. And the compacts, it's a two-sided canonical ideal that I'll be talking about in a moment. And this one here is then the summary that I mentioned, that my work with Reinhard Werner gives for the universal C-star CUNTZ Q C-star algebra isomorphism of one onto the other for Q in that interval here. And the big conjecture is how much bigger can you make that interval? And I guess on good days, our conjecture is in the whole open interval, but probably that's too optimistic. Okay.
Sorry, is there any specific Q which is larger than square root of 2 minus 1, for which it is also true, or?
Only if you go to the Fock representation. In that case, you can do it, yes. I believe for the universal representation, it's this is the best. And so, as I said, Voiculescu had some of his students try to improve it, and that wasn't.
No, but
visible.
I'm not asking about improving the whole interval, but about a specific number, like an isolated point, Q.
The answer is no.
No, okay. Thank you.
So that if you are fascinated by that, that would be a good one to do. Right. So in many ways, a single Q is really important because it would say that some of the structure here behaves differently and it's quite possible. I mean, there are other questions where you might have some isolated points where you have it and but not for all, and that would be quite typical of what you often see in commutative analysis, where you have fractal measures and parameter and
I'm asking this question since there are several phenomena, for example, for this irrational rotation algebra,
yes,
torus, which has nothing to do about the size of this parameter, but rather the measure of irrationality
yes, absolutely. So this would be absolutely fantastic if we get some more structure on the Q parameter here, so that so we really, even Q rational versus irrational, we don't really have any special way to identify that for the C-star algebra in a way that I know the irrational rotation algebra and the mutually singular and all of that, and the right. So the as of now, there's no subclass of Q parameters that is known to have better properties than the others. Okay, so that was
Marek,
that.
you wanted to ask something because you waved hand.
I have some question, if it's possible.
Yes.
So my main question, I don't remember well, but is problem if that C-star algebra generated by Q commutation relation as a creation annihilation, it is nuclear or not? That means if the C-star algebra and the in Fogg representation are the isomorphic or not? How is that problem?
I'm pretty sure that in the Fogg representations, it's nuclear. I strongly
for Fogg, but for universal,
I strongly suspect that it's not nuclear for the universal.
Not nuclear. So still open. Thank you, because that question,
I think so.
I remember 30 years ago.
Right.
Thank you very much.
There's so many.
The problem is important because
so many exciting
in the
open
quantum
questions.
groups use just universal C-star algebra.
Yeah.
But here is the same problem. Thank you.
Right. Yeah. So many interesting open questions, and some of them have been open for a long time. Yeah.
Yeah, of course.
And this one here is just mentioning the first two bullet points, repeating what I said, and the third bullet point is that if you are willing to go to the Fogg representation, then you can get a bigger Q interval. by Dagmar and Nika and others too, including myself, actually. And I'll get to that when we get to the. Okay, this one here, I believe we already talked about from bosons and the special role of 1 minus Q, and the coherent states give new representations, and so I'd like to come back to the coherent states shortly, and so I mentioned a little bit about the answer to these two bullet points here. If you look at coherent representations indexed by a vector, And if the vector has norm strictly smaller than 1, the current representation is equivalent to the vacuum Fock representation. However, if the norm of the generating vector is equal to 1, you get a non-Fock representation, and as you vary the vectors with norm 1, you get mutually singular representations or mutually inequivalent representations, or mutually disjoint representations. So those are 3 names for the same thing. Okay, and here's the two-sided idea. I'll get to the details of that in the detail part here. So this is just a reminder. And the other one was a reminder about the quotient construction. And this was a reminder about the motivation from physics coming from q equal to -1. And why we put in that modifying factor 1 minus q so that we get an algebra of bounded operators. Maybe I'll just mention one more thing about both the canonical commutation and anti-commutation relation. If you have the space H to be finite dimensional, then the CC, then every representation of the commutation relation is unitarily, any pair are unitarily equivalent. That's the Stone von Neumann uniqueness, but that would be false in infinite dimensions. However, we still have a CCR C-star algebra, and that C-star algebra would have many inequivalent representations. And the same is true for the anti-commutation relations. You know that the CARs can be realized in an infinite tensor product of the 2x2 matrices, and the quantum states are trace 1 operators. And if you take a diagonal operator in each of the tensor slot, lambda 1 minus lambda, and then do the tensor construction, then the theorem of Bob Powers is that you get a type 3 lambda factors, and they are mutually singular. So that was a big breakthrough. And the breakthrough for 3 1 factors came a little later by Ufago. And so that's one more connection to classical theory.
Sorry, you have said that those factors are mutually singular. You meant mutually non-isomorphic, yes?
Yeah, that's what I should have said. Yeah, so the Powers factors are mutually non-isomorphic. So the big theorem of Powers was a lambda family of non-isomorphic factors. Yeah.
Can I say 1 word?
Yeah.
I think in like 5-10 years ago, we worked with Zhenya Litvinov and Janusz Wysoczański, and we extended Q relation to Q of modulus less than 1. This is
yes.
That in some, I don't know, we know that is some in that sense because it's an unbounded operator, but we extended, and there is a series of paper in many journals by myself, Wysoczański, and Litvinov. So I don't know how is in your, also quantum noise and the other business was done, but what for me was surprising that for O disk, we have not only for Q plus minus 1, that is but also for modulus 1 we extended.
Okay, so that's exciting.
That is delicate. You using, then you have the formation what you started with your colleague, which so-called you use operator Young-Baxter. So we found special Young-Baxter operator for that business. Anyway, so I don't interrupt you, but please.
No, that's good. I'm glad you mentioned it. I will certainly look at your papers again. I've learned a lot from your papers, and so I'm looking forward to also study the new ones. And it's good that you call attention so that the other members of the audience are motivated to look at them as well. Okay.
Anyway, for mention.
Thanks. Yeah. So that's the second bullet point here. Really exciting and current work by Merrick and others. Yeah, very good. Yeah. Okay, and so these are the unsolved questions, and I think I mentioned them as well. We have not worked so much about Q versions for the unbounded operators, but I guess for the Fock representations, the unbounded operators would probably be perfectly fine, and we have the basic Hilbert Fock representation exponential construction working for the Qs as well, where you then introduce Q factorials and Q binomial coefficients, and that's exciting, but we haven't done it. So finally here I get to a few more details about the technical points for the thing I mentioned in the first slide here. And the main technical point that I call attention to in this proposition here is not all these ideals, but a particular canonical one. And so you take your Q relations as we defined in the beginning and now in equation number 1, and you take an orthogonal system of unit vectors in the generating Hilbert space, and then you work in that algebra. So again, we're talking about an algebra on generators and relations in the sense of CUNTZ here. That algebra, of course, can as Fock representation and so on, but I'm not going to do them yet. I'm just going to look at that algebra, and number 2 is saying that from the Q relations, it follows that in the order of star algebras, you have number 2 satisfied, which means that you can look at the element 1 minus that sum as an element in that star algebra. And that element can be shown to generate a two-sided ideal that's canonically isomorphic to the compact operators. And that means that if you do the Q algebra divided out by that ideal, then you get a canonical algebra. That canonical algebra is the one that we call here with a tilde, and that would be the analog of the CUNTZ algebra for the special case when Q is equal to 0. And furthermore, the representation of the quotient algebra is not realized in the Fock space. So you have to come up with different ways of realizing that, and that's why we started the coherent representations. But I should just in the last 3 lines point out what it means to be canonical. What it means is that we have the quotient map of the CUNTZ tuplets Q algebra here onto the quotient, and if you define it this way here, then it says every representation passes to the quotient here, and so that's the sense in which is the universal algebra.
Sorry, I'm a little bit confused about the way in which this proposition is formulated.
Yeah.
In the first part, you have written that then there is a C-star algebra, and in this first part, you are not saying that this one is universal. So I'm a little bit confused.
So it's only the quotient that's universal.
Yes. So why algebra by EH of Q, which could be in fact any algebra in which this relation is satisfied? Yes. So
yeah, I'm a bit
confused.
But the first one here is realized in the Fock space, and then you identify this ideal and pass to the quotient, and that's how you get the universal algebra.
Okay. So this is concretely represented.
Right. So the top half of the proposition is concretely represented, and it's only when you identify that two-sided ideal and pass to the quotient that you get a universal algebra.
Okay. I think that I understand now. Thank you.
Okay. That's an very important point. And it's also an important point that even though the Q algebra in the top of the slide is canonically represented in the Q Fock space here, when you pass to this quotient, it's no longer realized as a representation in the Q-Fock space. So we have to understand it in different ways. But it's still non-type 1, so it has right, it has all the non-type 1 representations. Here, the next one is standard because of the commutation relations. You can always arrange that the elements in your algebra have the dagger on the left, so you can have a monomial in the dagger generators and the others, and so in physics they usually call creation and annihilation, written as monomials this way, and then it's enough to define the state on those monomials. So monomials are usually called the Wick ordered elements, and that also works by the exact same argument from physics, that you can always find a dense a dense element of weak ordered, and that helps a lot in understanding properties of representations of the Q algebras. And so we'll be looking for the coherent representations. We'll be looking for identifying positive linear functionals, and these positive linear functionals would be realized first in the Q-Fock representation, and then we'll study passing to the quotient later. Okay, and this one here is, I think we talked about all of that. And the last bullet point I mentioned before is that for some representation theory questions, it's important to look at a continuous field of C-star algebras and then study physics types questions of the quantum phenomenon that arises a direct integral over the Q parameter. So it is possible to build operators that play a role in physics as a direct integral over the Q parameter. So that's all that is mentioned. Serve to mention this one here. I'm really excited about. If you look at the Q relations, and you divide by Q and let Q go to infinity, then you get this relation here. And this relation is really just saying that, so if you have unit vectors, you have isometries, and so here you have a very special kind of coherent relation here. But the exciting thing here is that if you have a representation of the first bullet point here, a dagger GAF equal to the inner product times the unit element in the algebra, if you have a representation of this, then you get a for Q smaller than 1, then you can take the reciprocal, and then you're in the interval outside here. And for this particular representation here, then you get a reflection system where the representation in the reflection comes this way here. The dagger on F goes into the A on F bar, where F bar can be any anti-unitary operator. And so that's an extra kind of reflection property that happens for the special case of the Q relations, Q equal to infinity. So in general, there's very little we know about Q, absolute value of Q bigger than 1, but Q equal to infinity is kind of different. And so this is something I think would also have importance in properties of quantum field theory. And so that's all I want to mention about this. And
may I have a question?
Yeah.
So 1 and -1 are the only fixed points of this mapping, which sends
Yes.
Q to Q -1. So
yeah, right.
The reason for expecting that those Qs different from -1 and 1 should eventually be not relevant in physics?
I didn't quite understand that. The last line.
So to put it in another words, so maybe since for 1 and -1, Q is the same as Q to -1, this is precisely the reason why Q equal to -1 and Q equal to 1 would be physical. Of course, I know it corresponds to fermions and
okay.
bosons. Maybe it could be
Yeah.
made.
Okay, I understand. I understand. That's an exciting direction to follow up on. Thanks. I guess I'm looking at this because reflection positivity in quantum field theory is a very important subject. You get different solutions to quantum field theory problems in different realizations in a different kind of reflection. So okay. Right. That's the weak order, and so now I'm at the the one where we introduce the coherent representation. So I mentioned that the coherent representation can be gotten from a state in where I use the word state in the sense of star algebras, a positive linear functional on the star algebra here, and so here's equation number 4 is equivalent to the other definition I gave of coherent representation, only that in equation number 4 I'm characterizing the state as opposed to characterizing the representation. But by GNS, we know that you can pick and choose, and so if you would like to compute the coherent state, then equation number 4 is what it looks like, and it's fairly easy to go back and forth between them. But equation number 4 has the advantage introducing the weak order, that we can directly construct these coherent states inductively using the weak order in the Q system. So and I don't have time to go into details of that. I'm excited about it because it will use Q factorials and Q binomial coefficients that I think they're exciting in combinatorics and in many other parts of mathematics. So there was one thing here, and I apologize for not having time to go into the technical details of it. The technical details are included in the papers that I cite here at the end. But the second one is the details behind what I said about the relationship between two coherent representations, each one of them indexed by a vector, the first one by a vector phi, and the second one by a vector psi. And so the answer is that if you look at these two coherent states here, indexed by one vector and indexed by the other vector, then we prove and we find the explicit element V that you have on the right-hand side here. V is, of course, then indexed by the two vectors because V is making a connection between them. But the thing that I want to emphasize here is that the last line is an explicit computation of what's called the C-star algebraic version of the Radha-Nikodym derivative. So you should think about the V vector as a quantum version of a Radha-Nikodym derivative.
May I have a quick question?
Yes.
I'm a little bit confused since you have written invertible element, but you use V star instead of V to -1. So should it be maybe unitary or?
Yes, if you are in the peripheral case, yes, but if you're in the non-peripheral case, the norm is strictly less than 1, then it's not invertible. So again, another misprint. I should have distinguished between those two cases. But you will see the formula for V.
So once again, this element is invertible, but still you want to have V star in this formula, or rather V2 minus 1, V inverse?
I don't want V inverse. I'll show you the formula later.
Okay.
And this one here is again a summary of the properties of the states here. And the Fock state is when the vector is 0, and when the norm is equal to 1, it's a peripheral state giving mutually disjoint representations. And here's just a terminology that we jump back and forth between the states and the representations, and the link between them is a GNS representation. And this discussion here would just be for the coherent states. And so this one here is the one where the norm is equal to 1. And again, this is a statement of a result that I don't have time to prove. But what you see is that if the norm is equal to 1, the coherent state is determined in a very easy manner like this, by its value on products of elements like this. And so that's a very special situation where you can determine the state by its value on its 2-point functions, but we're still in the Q relation case. And the details of proof in the paper that I cite here, and the corresponding GNF representation would vanish on this ideal that we want to divide out by. And so that's that. And so it's a little funny in my here. Okay. Oh, okay. So I have it in my. I have a printout of it in front of me here. And this one here is just fleshing out what I mentioned before about this canonical largest ideal and passing to the quotient. And so the quotient algebra would be the universal algebra, and yeah. Let's see. Oh yeah, the conjecture, of course, is isomorphism of the canonical algebras, as opposed to just the algebras coming from the relations realized in the Fock space. So that's a clarification of what the conjecture means. And but even if the algebras are isomorphic, we still have many inequivalent representations and many non-isomorphic for Neumann algebras, is what I say in the bottom of the page. And now finally I get to some of the yeah.
Just a sanity check. So it could happen, yes, that the von Neumann algebras are non-isomorphic, since it involves taking bicommutants, and this bicomutant somehow takes care about where this algebra in fact is situated in this large Hilbert space, in B of this large Hilbert space.
Absolutely. Yeah.
Mm-hmm. Mm-hmm. But still it is very strange.
Yeah. But anyway, I guess there's some technical details where I would have to refer to the detailed proofs in the paper that I cite.
Could you please go back to the previous slide? I have a question.
Yes.
So what I'd like to see, you see, when you think about the CUNTZ algebra, you have this natural number bigger or equal to 2. And I don't see it here. When you say CUNTZ algebra, it's CUNTZ algebra for each number.
Or the
here I allow
I understand that it's a family, right? Because you had these...
right. So it's you fix D and then you allow a Q family.
Yes.
And the Q family of interest is of interest, as I mentioned, both for D equal to 1 for D finite bigger than 1, and for D infinity, and they have slightly different properties. If D is equal to 1, we get the Q harmonic oscillator, where the single generator has this weighted shift property. And for D bigger than 1, we get canonical isomorphism with the better known CUNTZ algebra for values of Q less than the square root of 2 minus 1. And for D equal to infinity, it's a little bit different because the representations in the Fock space behave a little bit differently. So the definition here is meant to cover all three cases: D equal to 1, D finite, and D infinite.
Okay. So it's a family of definitions, in fact.
Right. Yeah, that's good. Yeah.
But I think that the question was about what is this D. So this D is the dimension of this Hilbert space.
Yes.
Yeah. But because we had this orthogonal basis cited earlier.
So we pick an orthonormal basis in the Hilbert space H, and if it's two-dimensional, then we get the CUNTZ algebra O2.
Yeah.
And if it's three-dimensional, we get the CUNTZ algebra O3.
Yeah, thank you.
And we also get Q versions of them.
Yeah.
Okay, so this one here, the purpose of this one here is, again, to look at the peripheral case and look at justification for the assertion that I made about inequivalent representations, meaning that they live in orthogonal subspaces, and these subspaces here can be constructed from certain family of operators P phi. I think the P phi's become projections here, and this is just a baby application of the ergodic theorem in Hilbert space, that the limit in equation 15 is the projection onto the vectors that are fixed by the operator a dagger, no, pi of a dagger, and so then you have a family of projections indexed by the peripheral vectors from the generating Hilbert space H here, and you have that the representation leaves invariant. The subspaces spanned by these projections here, and the last line here is helping you to understand why, if you restrict the representation to two different subspaces, one indexed by phi and the other indexed by psi, they'll be mutually orthogonal. And if phi is equal to psi, it'll just be the coherent representation in that subspace coming from that vector phi. So that's all that's supposed to give us. So it gives us a way to understand an index family of these special peripheral representations. And if you follow up with more detailed technical computations, you would also be able to use the last line here to verify that for distinct unit vectors, you'll get inequivalent representations like this. And so this is more about these peripheral here, where the norm of the generating vector is equal to 1. And by using a little bit of combinatorics, you can show that for this case, the coherent state on that algebra is determined by equation number 1. So it's very easy it's a lot easier to compute it for the peripheral ones, for the ones where the generating vector has norm 1. And it's also a little combinatorics to show that that the canonical ideal is contained in the kernel of the representation. That I will not do in detail here because I'm going to run out of time. Then we get to another fairly complicated, but I mentioned most of the details in that definition already here, but maybe we'll just concentrate on the first 3 lines here. The q-CUNTZ algebra is the one you get after you divide out by the canonical ideal, and so there are 2 Q algebras, one before you divide by the ideal and one after you divide by, and so we just make that precise. The rest of this discussion here, I think I mentioned that already, the distinction between the Fock representation before you divide out by the ideal, and that the universal algebra you get by dividing out with the ideal does not admit a representation in the Fock space, and again about the different phenomenal algebras as you vary Q. Okay, okay, so that's and this one here is repeated. Here finally I get to the canonical ideal and a very important element. So again, we go back to the Q algebra, and then remember, okay, so remember on the left-hand side in the Q relation, we have A first, and on the right-hand side, we have A dagger first. So then I look at an orthonormal system, EI, and then I look at this element rho here, and that play an important role, and that element is obviously in the Q algebra before we divide out by the ideal. But the main thing that goes into our proof of the conjecture for small q is that the isomorphism between the C-star algebras for q different from 0 and for q equal to 0 is gotten by doing a fixed point theorem where the bounds that we need in the fixed point theorem depend on q, and that's the secret to why q has to be less than the square root of 2 minus 1. But now, before I can get to that, I have to introduce the special element rho that's defined this way, and it is in the Q algebra here. And I also have to okay, the conjecture is then that there is a C-star isomorphism from the 0 algebra to the Q algebra here. And in a special case, when we can construct it, it'll be constructed this way here, coming from an isomorphism eta that we took look at here. So eta so the V generators are the generators of the standard CUNTZ algebra for q equal to 0, and the A elements are the generators of the Q algebra. And so we construct C-star isomorphism for special values of Q that takes you from the 0 algebra to the Q algebra. And then you apply that to get into the Q algebra. And then once you are in the Q algebra, you multiply by Q, by rho here, and then you get a new element, a dagger. And so the theorem is proved this way here by constructing by using combinatorics of the Q relations, such as C-star isomorphism for small values of Q from the 0 algebra to the Q algebra, and then the explicit formula that relates the generators in the CUNTZ algebra, V dagger, to the generators of the Q algebra, A dagger, would then be determined this way here. So it depends on 2 things. First, the element rho here, and secondly, construction of such a C-star isomorphism, which we do by an application of a fixed point argument that requires an estimate that is equivalent to absolute Q less than the square root of 2 minus 1. So that's the main thing that I want to say about that one here. Right, so then I think I better go to the next because I'm running out of time here.
Yeah, you have minus 4 minutes.
Oh, okay. So maybe the next, yeah, the main thing here is just elaborating a little bit about what I said before. And so what I said before was that we want to get our hands on this magical element rho. And then after we get that, then you will see how that magical element rho takes you from the zero algebra to the Q algebra. So it takes you from the the standard CUNTZ algebra to the Q version of the CUNTZ algebra. And it takes the generators in the standard CUNTZ algebra, VI star, the VIs, and you multiply by that magical element rho from the previous slide, and then you get the generators for the Q algebra here. And so that's the main thing I want to say about that one here. And again, the second to the last line is again calling attention to the two-sided ideal. And so it looks like I'm out of time. And so I think it's better that I stop now. And if there are questions, we can move on to the, yes. So here again, mentioned Dijkema and Nijker for extending the Q interval in the Fock representation. And here I mentioned the a priori estimates that depend on Q that go into our proof of the isomorphism, and the boundary discussion here, and some special discussion about Q equal to 1. And this is the one that I want to call attention to. For the general theory of infinite dimensional analysis related to Q versions of the Fock representation, there's a book here that's only a couple of years old with my colleague James Chiang. He was a former PhD student of mine. And then I have 2 papers joint with Selmienko and Pozorskin, which deal with extending the Q interval, but only in the Fock representation. And then finally, I have 3 papers joint with Reinhard Werner, whom I mentioned in the beginning. He's one of the pioneers in quantum computing now. And then the last one here is an early paper where I did a systematic study of representations in Hilbert spaces and dilated Hilbert spaces that includes these particular relations here. So that's what I have to say. And if there's discussion points, I'd love to stay for discussion.
Thank you very much. Thank you for a very beautiful talk. Thank you.
Thank you very much. And thank you for all the wonderful questions. So I'm so happy because I learned a lot from the questions. Yeah.
I have a bunch of questions, but maybe I shouldn't be first to ask. So,
okay.
Marek, maybe you want to begin.
Oh, anyway.
Oh, by the way, I should mention that the papers by Brzezinski, Speicher, and many others are included in the papers that I cite here. So if you want to look at the background papers, including Brzezinski, Speicher, and others, just take a look at my papers with Reinhard Werner. And
anyway,
so I definitely
thank
want
you
to
very much that you recall me what was like 40 years ago, 30 years ago. And that was my best time when I was with Hagerup. I think you don't mention Uffe Hagerup, but he was, how to say, the most important person because he started not with CUNTZ algebra, he started with free group. Maybe
yes, you're right.
And he proved main result about free group, and that was extended by Wojkulescu to free probability. Also, I did.
That's right.
And that was the so. For example, your coherent state. This is really theorem of Hagerup. I think also in Wrocław, Pytlik, Schwarz, and myself when we worked for Z to the length function on free group. And that was our coherent state, and that was extended to more general case to semi-group because CUNTZ algebra is nothing else like semi-group. algebra.
Yes.
So free
So
semigroup, of course.
right, yeah,
So it's much simpler, but it's
mention.
equivalent for many questions. So this is my
Right.
only general. But we
Right.
are very follow your paper with especially I remember paper
yes.
coherent with Werner and Smith, and I remember I was on other conference with Professor Voronovich, and he said, Marek, you should study that paper. And even more, he gave me a paper to make referee. I don't remember which journal. So, but this was 30 years ago. I can say this.
Yeah.
So Voronovich say it's very good paper, but Marek, you should check it details.
Yeah, that's right.
And we check it, and that anyway, we just come to your paper, especially to that paper with Smith and Werner, very important. For that business, and I think you mentioned many results from that paper, if I remember.
Yeah, right. I should
thank
also
you once
say
more, Palle, and thank you also, Piotr, that he invited you for such.
Thanks,
And I hope.
But I just want to mention two things. One is that from my first life in Denmark, Hagerup was a very, very good friend, and I'm so impressed with it. Is one of the top mathematicians in the whole world, and he died tragically a couple of years ago in an accident, drowning accident, and maybe say that we talked about a Danish piece. We used to have jokes about asking people to pronounce Hagerup's name in Danish, and no one could. And so that was the other thing. And the other thing from my first life in Denmark was that at that time, Rich would come often to visit us in Aarhus, and I have fond memories of that.
Anyway, thank you once more, Palle. And
right, thanks.
Any other questions? Adam, Tomek?
Yes, I have one question.
Yes.
It could be difficult, I don't know. There is this notion of Gromov-Hausdorff distance, and I wonder whether this family is continuous in this Gromov-Hausdorff distance of this Q deformation.
Oh, right. That's fascinating. We should look at that. And I've not looked at it, so I don't have answers. So if you looked at it, you know more than I do.
But Mark Riefel just told me that he knows you very well, so you should guys communicate.
Right. I should say that the Gromov-Hausdorff distance comes up in some work that I do on analysis on fractal, but that's sort of in commutative harmonic analysis. And you might know that some years ago, I got interested in whether you could make orthogonal Fourier expansions on some of these self-similar fractal measures, and I managed to do it, and I didn't know if anyone would be interested, but it turns out that the top person in harmonic analysis, Bob Strickert, was super interested, and so he kind of took up that and invited me to give conference talks. And so my work on harmonic analysis on self-similar fractals got a lot of attention. But and of course, that Gromov-Hausdorff distance plays a role in that too. But there might even be analogs in the non-commutative version here that I hadn't thought of.
Yes, there are.
Yeah.
This theory is... I think it's very much developed by Frédéric Lattre-Molière. I'm sorry for...
Oh, right. Yes. I have looked at his papers a little bit. Yes, you're right. Absolutely. Yes. It's just my it's my fault that I haven't followed up on all the things I should follow up on. But yes, now that you remind me, I did look at those papers, and I tried to understand them as best I could, but I didn't do nearly enough.
After introducing this 1 minus q, which forces your operator to be bounded, I think that there could be some hope for this continuity.
Yeah.
Fantastic. That would be really, that would be really great. Yeah. Mm-hmm.
Okay, Tomek.
Okay, I have a question. Maybe Marek Bożejko could help me with canonical commutation relations. There's associated some family of self-adjoint operators, some canonical operators Marek was interested in. And there is some non-commutative probability theory about this.
Yes.
And there is some functional which is defined in the context of this self-adjoint operator.
Yeah.
And what we did some times ago with Łukasz Kaczmarczyk, we found an asymptotics. When you replace one particle Hilbert space by the number of particles increasing.
Ah.
And you start, what is interesting is you start from this semicircle law.
Yeah.
At the beginning, but then it starts deforming. And finally, we found very strange phenomenon that this measure, in a sense, this non-commutative measure,
yeah,
asymptotically tends to the Haar measure on the boundary of the quantum disk.
Oh, fantastic.
So we don't understand this result. We cannot interpret it.
But what do you mean Haar measure on the quantum disk? It's not a quantum group, so.
Yeah.
Sorry?
Yeah.
What do you mean by the Haar measure of the quantum disk?
No, on the boundary of the quantum disk.
Which is a circle. Okay.
Yeah, because the Teplitz algebra could be identified with a disk. And then you are starting deformity, Q deformity.
Yeah.
Okay? Then you have this family of states,
right,
which could be interpreted as a family of non-commutative
right.
measures. And asymptotics, when you go into this this part of the Fock space, when the number of particles tends to infinity, concentrates asymptotically on the boundary of this Teplitz disk.
That's really exciting, yeah.
And it's nothing else but Haar measure.
Yeah,
but we don't understand what could be the reason of appearing this asymptotic symmetry.
Yeah, it reminds me a little of some of the boundary questions in Drury-Arvison. The kernel so if you have kernel representations, you want to do a direct integral by a measure on the boundary. In your case, that would be a Haar measure, and those in my general. So I have work on representations built from kernels, and some questions about boundary can be very difficult. I know in some particular cases. Yeah.
Yeah, we expected something fractal in the limit, but
yes. Question, because we prove that Q-Gaussian, what you call creation plus annihilation,
Yes.
This is self-adjoint and satisfy for Q equal 1 Gauss, for Q0 Wigner, for Q minus 1 Bernoulli, and between this is so famous theta function of Jacobi.
Yes, you're absolutely right.
You know, is very low, but what is important that measure is absolutely continuous with respect, let's say, Lebesgue measure on the circle, and we prove this, that is the estimation from below is important for that operator that doesn't depend on Q. And there is, I don't know, also there is a paper, Alexander Nu wrote serious paper, maybe you know, from he is from Besançon now, he's student of Q. Also, I mentioned now Eric Ricard, also from Besançon. He proved factoriality for that algebra generated by Gaussian, Q-Gaussian. This was open question. We prove only special case. So, and that asymptotic, I think, is maybe also you found in our paper with Janusz Wysochański and Litvinov, when we consider Q relation for Q of modulus 1 or even less.
Yes.
We don't check it the measure, but that should be analytic continuation of course of theta function of Jacobi, which is also
that would be fantastic.
But
yeah.
we have no paper, but I am sure that your question it will be solved. And if you have paper, please send me, or maybe come to Wrocław seminar if you have time.
Right.
We have no Zoom. We have classical seminar each Thursday.
I'd love to visit. travel is a little more difficult now, but I'd love to. I have so many fun memories of visiting Poland, going back a long time.
No, but mathematics
but
is personal
Yeah,
game.
that's right. I
Personal
totally agree. Yeah,
is not only Zoom. Zoom is
yeah,
very useful. You may give idea, but
yeah. I agree.
you should work.
Yeah,
So that personal anyway. But this
So,
yeah, right.
I know that Piotr Hayacki has different approach. He says that just such a seminarium on Zoom is the best. Yeah, but
I don't know.
no. Don't
no.
put words into my mouth. I
But
believe in hybrid. So as much as
Hybrid.
possible,
Yeah,
we
of
have
course, of course.
speakers on
yeah,
site,
right.
Yeah.
Yeah, but
and
we'll do the best we can. We
we do
have
the
to
best we can. And when I can have
improvise.
a super speaker who cannot be
Sorry,
on site,
sorry.
I prefer a super speaker on
I
site than
don't
a random
input your word.
person,
No.
a super speaker online than a random person on site. So
So
I think
if
that's an important
yeah,
change.
no, Piotr, sorry, I don't want to push you. Anyway, I only say that next July from
Yes.
6 to 12 we organize Bendlevo meeting on non-commutative business of that Q business
Yeah.
and QR quantum groups when Ania Kula-Wysoczański and
Oh, yeah.
Janusz and other people. So welcome
Yeah.
to Bendlevo meeting. This is our anniversary, 20 Bendlevo. It's not
Yeah,
so
I hope to come, but let's go back to the
welcome
questions.
everybody.
Right.
Yeah.
Okay, very good. It's good. Yeah. So,
Tomek, are you
right.
happy now?
maybe I should
No, we should
specify
maybe
something.
personally discuss more.
Yeah.
It's all right. But I guess Tomak was kind of an example of getting good boundary representations where boundary has to be understood in a way that's complicated. It's a question that sort of fits into the theory of potentials and potential boundaries, and those are typical difficult questions.
Okay, so can I now ask a question? Or?
Yes.
Okay, so but I have to write it down.
Yes.
You see, one of the reasons we got recently so excited about CUNTZ algebras was because we looked at morphisms. So,
Yes.
but before I do it, let me ask you the following question. So I will try to follow your notation, but instead of writing the Hilbert space, let me write its dimension because it tells you more.
Yes.
And here I write this Q, okay? And then basically what you do, you quotient it by compact operator, so you have a short exact sequence. I'm sorry, I'm writing with a mouse.
No, I see exactly what you're saying, yeah.
Okay, and now I go to the q-CUNTZ.
Yes, absolutely.
So D and Q.
Yes.
All right, and my first question is the following. When I look at, because the K-theory of CUNTZ algebras is very specific, very beautiful. So can you at least, of course, when you have an isomorphism, they are good. But if you don't know for this Q, which is too big, if I take this q-CUNTZ sister algebra, ODQ, can I at least say what its K-theory is? Does it coincide with the CUNTZ algebra K-theory?
It's difficult. I mean, one of the ways to understand the difference between the community and d equal to 1 and so we have the classical triplets, and you get an extension. The classical triplets algebra is an extension of the function by the compact, and it's given by the index of the triplets operator, and so you have a winding number, and so the winding number is the beginning of a K-theory here, but I do not even know an analog of a winding number for the universal q-CUNTZ algebra that you write in the first line. So maybe to get started on some kind of answer to your question, maybe an analog of a winding number would give us at least some good guess on what K-theory might look like.
And another question in the same spirit, because I'm simply asking simpler questions, right?
Oh, I see. I should say that CUNTZ became famous because he computed K-theory for the standard CUNTZ algebra.
Yeah.
How does CUNTZ's theorem about the K-theory for his standard Q equal to 0 CUNTZ algebra, how does that K-theory extend to the Q case?
Yeah.
And I'm glad you asked it, but I'm afraid I don't know the answer.
Okay, and in the same spirit, can you at least
Piotr,
say
I
that
have to leave. So thank you once more, Palle, and everybody.
Okay.
I have
Thank you,
Marek.
I'm so happy to see you
Bye
again.
bye.
So many
Bye.
fond
Thank you, and
memories.
we
Thanks.
contact with Tomek about your business. Thank you very much.
Thank you.
Maybe
Thank
after
you.
New Year. Thank you. Happy New
Okay.
Year and everything nice.
Okay, good. Yeah. Thanks very much.
Bye-bye.
Yeah. Thanks. Yeah.
And another question is, how about the simplicity? Can you, even when Q is too big to claim an isomorphism, can you still conclude that these sister algebras are simple?
It's one of the questions that I think the answer is yes, but I don't have a proof.
Okay. And now I'm coming to my real questions.
Okay.
So this is just a warm-up. You see, how about morphisms? So let me write here some, which letter say C, right? CD. I write OCQ, because you see, when you put Q equal to 0, and then these are really the CUNTZ algebras, then you know by K theory that if D and C satisfy a certain congruence relation, then there is a star homomorphism. Of course, it has to be injective, unital star homomorphism.
Yes.
And in general, we are in the realm of Kirchberg and Phillips, which says that for a given class of sister algebras, if K theory allows a star homomorphism, then it exists.
Right. Yes.
This is a non-constructive theorem, and so what we are looking at constructions of the star homomorphism. So that particular construction was unraveled by Kawamura, but it also follows immediately from the graph theory. So my first question is: imagine that I have such morphisms as described by Kawamura, as allowed by the K theory, when the congruence relation between D and C is satisfied. Do they lift? Do they lift to star homomorphisms between your extensions?
Yeah. Again, it's a fascinating question, and I do not have an answer. But the next question is if I have some intuitive feeling of whether it extends. I think it could be. Maybe it could be very difficult because of the non-type 1, and so if I should make an a rough guess, I would think not.
Because you see, when Q is small enough, you know that this morphisms exists.
Oh, right, yeah.
And then you know the K theory of the left and right component. So by the sixth term, you can compute the K theory of these extensions.
Oh, that's true.
And then maybe you can see if K theory allows the same. I mean, if the same congruence is implied by K theory. This will be the first exercise to do.
Okay. So maybe the sixth term would allow you to do it.
Yeah. So that would be my immediate guess. And finally, because at a certain moment you mentioned matrices over CUNTZ algebras.
Yes.
Where recently with Young we have a certain new result, I believe. Namely, we were looking at embeddings of CUNTZ algebras, but not in CUNTZ algebras. But in matrices over CUNTZ algebras.
Very good. Yes.
And again, it's covered by Kirchberg and Phillips. However, we did it constructively. So now there's a slightly more general congruence relation. Okay.
Right.
And then we explicitly construct. And what is nice, I believe, that we have polynomial expressions. We have polynomial expressions embedding a CUNTZ algebra in matrices of a CUNTZ algebra. Using graph sister algebra. So I mentioned it because you mentioned matrices at the
same. We do use the matrices for understanding the positivity condition for the states.
Okay. So that's all from me.
Thanks.
Anybody else? Any last call, final call questions? Okay, I don't see it. So let's thank Palle again for a very beautiful talk. Thank you so much.
And thank you again, back. Wonderful questions and wonderful audience. And so I'm so happy
Thank you.
to meet you again. And so we'll continue. But so thanks and happy holidays. And I'll click stop sharing. Okay.
Yeah, and I click stop recording.
Yeah.